Hi, everyone. Welcome back to E54. Today, we'll be going over lecture 12, and this is where we start to introduce polymers. So the primary issues we're going to address are similar to what we saw for metals and ceramics. We're going to talk a lot about the structure, and we'll see places where it's different and has some similarities with those other materials. And then we'll also talk about the properties. Now, in terms of properties, I'll mainly focus on mechanical, but again, we'll try to make some comparisons and contrast the different behavior. So the first thing to do is recognize what this word polymer means. We can break this down, and the poly means many, and the mer means this repeating unit. Okay, so we have many of these mers. What I'm showing on this slide is three very common polymers: polyethylene, which is sometimes just called PE, polyvinyl chloride, which is called PVC, and polypropylene, which is PP. Now, these are things you have probably seen many, many times in your everyday life. Just as an example, polyethylene can be used to make many things. One example is something like a little plastic baggie. PVC is, if you, for example, you look underneath your kitchen or your bathroom sink, you'll almost always see these pipes, which are made out of PVC. And then polypropylene is used for a wide variety of things. I just selected a few examples. These are sort of shipping crates, storage containers, and sort of plastic lawn chair type of things. There's many different types of polymers. We won't sort of go through an exhaustive list. I did just want to point out, though, that there's ancient examples of natural polymers that have been used for thousands of years. Some of these include things like wood, cotton, and leather, or rubber, wool, and silk. So these would technically fall into the polymer category of our different materials we're talking about. And just an example of a known use, so rubber balls were used by the Incas back in about 1600 BC. So this is material that's been around for thousands of years. We'll talk about a lot of different polymer types. One of the major classifiers we can apply to a polymer material is we can say that it's an elastomer. So a good example, a well-known example of this is something that's rubber, okay? These tend to be cross-linked materials, which we'll describe a little bit later in more detail. But I want to point out that there's many different types of rubber. So we can have natural rubber. This comes from the rubber tree. We can have synthetic versions of this, where we make this butadiene be the main repeating unit mer in a synthetic rubber. Or we can have other things like silicone rubber. Good example of this is, I mentioned that you have PVC pipes underneath your sink. You might have silicone rubber caulking around your sink or your bathtub to try to make a watertight seal. You can also have fiber-based polymer materials. And here, a sort of general rule of thumb is that the length of the polymer fibers need to be 100 times or more than the diameter. The main use of this is in textiles. So generally, we want these things to have high tensile strength. They tend to be highly crystalline and have highly polar directional bonds. The most common way of making these fiber polymers is through spinning. And a good example is using a spinneret to extrude these long fibers. Examples being things like nylon or rayon, where these are used to then make clothes. Another sort of more high-tech example is Kevlar. So here, the repeating unit is outlined here, but this is forming some long fiber chain that can be used to make this bulletproof vest. Now, this repeating unit is relatively heavy, which ends up giving these long this polymer made of these long fibers, the property that it can be resistant to things like gunshots. There's lots of other different ways you can classify polymers. I'm just listing a few here. You can have coatings, so a thin film on a surface. A good example of this would be paint or varnish if you're used to using this. So what this does is it protects your item. It can improve the appearance, but it can also have a practical effect. The example being that it can provide electrical insulation. So if you look at wires that you have in your house, they're made of metal because those metals are good conductors, but they're coated with a polymer coating so that you only conduct electricity through the wire and not out in all the other directions. So you could grab that wire with your hand, you've grabbed the coating, and you're not going to get electrocuted. Polymers are also commonly used as adhesives, so they can produce a bond between two different materials. So things like glues are going to be good examples of this. And this bonding usually comes around through secondary bonds and mechanical bonding between the different adherents you're trying to put together. You can also have other examples of films done by things like glass blowing, or foams where you have gas bubbles put into the plastic. In this last case, a foam structure might be useful if you want to have a really low density material. One thing I want to point out is those early examples I gave were sort of low tech uses. So, piping in your kitchen, bags and lawn chairs. But these same polymers can be used for advanced applications too. So I gave you the example of the little plastic bag for polyethylene. Now, if you make a different type, and we'll talk about what exactly this means, but it's ultra high molecular weight polyethylene. This is what's used as the sort of replacement for your hip joint. So the metal socket or metal ball goes into this socket. And the reason is that this thing has low friction coefficient. So you can find lots of examples, things like hip joints, bulletproof vests, golf ball covers, that can give you wide property ranges that can be used in many applications. So one of the first ways we can start to describe that structure of a polymer is by the composition of the polymer, okay? So let's start by thinking about some of the basics. So for example, most polymers are made of hydrocarbons, which just means that they're made up of combinations of hydrogen and carbon atoms. But one classification we can use is you can have polymers that are saturated hydrocarbons. And what this means is that every carbon is singly bonded to 4 other atoms. This is shown as an example for ethane, which is C2H6. Here, if you look at each of the copper, so this copper is connected here, 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 here. So it has 4 single bonds. And that's true for all the carbon atoms. So this is a saturated hydrocarbon. A good example of this is the paraffin family. So things like methane, ethane, propane are just building up different saturated carbon structures. So this first one is just 1 carbon with 4 hydrogens around it. Now we have 2 carbons, 3 carbons, and so on and so forth. And we can build up these longer and longer molecules, keeping those same sets of single bonds. Now that's not the only option. We can also have unsaturated hydrocarbons where we have double and triple bonds. Now, sometimes these tend to be unstable because that means we can form new bonds. But good examples are ethene, which is C2H4. This molecule is shown, the chemical formula of that molecule is shown here in the middle. So here, the carbon is connected to 2 hydrogen, but it forms a double bond with the other carbon. If we look at acetylene, this has a triple bond between the 2 carbon atoms. Even within 2 compounds of the same chemical formula, we can have different structures, and this is called isomerism. A good example is for C8H18. You can have 2 different structures. You can have normal octane structure. So this forms a very simple structure. So there's carbon along the middle, the hydrogens come off to the side, and that's one way of putting together with this chemical formula. But you can also have what's called this 2,4-dimethylhexane. You could see it's a more complex structure where we have some side chains coming off in either direction. These both have the same chemical formula, but these are different isomers of that C8H18. In terms of common hydrocarbon groups, we can start to describe common trends we see. For what this table right here is showing is different families and their characteristic unit. So things we've probably heard, things like alcohols, ethers, acids, aromatic hydrocarbons can be built up. And that generally, as we go down, we're having more and more complexity. But what I want to point out is that this little characteristic unit, you can think of the stuff, the oxygen and hydrogen are sort of what's given, and what's listed as R can change and can be different organic groups. So for example, if this R is replaced by CH3, which is methyl, we'll get methyl alcohol. So it has that methyl unit and then that OH unit off to the side. Just to show another example for this ether, it has R and R prime. This is just showing that these don't necessarily have to be the same. In this case right here, this is putting two of those methyl units, one on the left, one on the right. We get dimethyl ether. So in this case, they're the same, but they don't have to be. And you can build up different types of examples of that. Once we have our starting unit, we can think a little bit about how this polymerization process happens. So really we can think about it as we need to have a catalyst or initiation site for our polymer to start, but then we can start to add on monomers to that. So this is that initiation step, showing our catalyst plus one monomer, and it has some dangling bonds over here. So we can imagine that we can continue to add more and more monomers to the end of this. So this initiation is the beginning of a polymer chain, and the propagation is as we keep adding on more of these monomers to the end. So this is polyethylene, and we're adding ethylene monomers. On this slide, what I'm showing you is the structure of that polyethylene. So on the top is that two-dimensional version we've seen with just letters being used for the different atoms that are there. One thing I want to point out is that this is it's very useful, but it's a simplified picture of what this polymer looks like. Actually, the way these things are put together can have a three-dimensional structure. So this is on the middle is showing that we have these little dumbbells of hydrogen atoms that are sticking out in opposite directions. Okay. Just to give you a sort of reference, if you go to page 486 in our textbook, you can find some images of common what we call bulk or commodity polymers. So you can see things like the polyethylene, polyvinyl chloride, and polypropylene that we talked about, but you can find other common examples of things that, again, you can find these at a hardware store or something like that. Now, to visualize that three-dimensional structure, I want to remind us all that this virtual material science and engineering can be a beautiful tool. If we go to our Wiley Plus site, click on MSE, for example, we can start to see and manipulate some of those three-dimensional structures. I'm going to pick something simple like PVC. And what this is showing is this is one unit of the PVC. So this is one mer. And I can add on more and more repeat units. And now I can see how this starts to build up. Right? I find this very helpful for visualizing those three-dimensional shapes, either along the polymer chain or what these side groups look like. So going back to our slides, once we know what our chemistry is of that starting unit, we can start to talk also about the molecular weight. So for different combinations of those MERs, we can have very few of those MERs put together or very many. So we can have either low molecular weight or high molecular weight versions of a given polymer. And what this is really talking about is what's the mass of a mole of these chains, okay? So if we have a given number of the chains, what would that mass be? Now, one important thing to point out is that when we're talking about a polymer having a low molecular weight or a high molecular weight, we're really talking about some sort of average, okay? In a real material, it's not going to be that there's hundreds of thousands of polymers with this exact number of repeating units. It's going to be that there's a distribution, and maybe this is representative of the average. Okay? So we really, this is showing that idea on the slide. So on the right here is a plot of, for a given polymer, which you might get if you measured all of the different chains inside of that material, you would find that there's some distribution. So if we make a plot on the y-axis being the amount of the polymer, and on the x-axis being the molecular weight, we'll see that, well, there's a few really low molecular weight chains, there's a few really high molecular weight chains, and there's some sort of number where most of our chains, or the most common value, is given right here. Okay. So because we have this distribution shown in red, we have to think a little bit about how we describe the molecular weight of a polymer. You'll commonly see it done in two different ways. You'll see either the number average or the weight average, okay? Basic idea here is we just count all of these as equal contributions. So if we have 500 different polymer chains in here, each of them is contributing 1/500 to that mean. Or do we weight that average by how heavy it is, okay? And the reason you would do this is that a heavy polymer chain is longer and it takes up more space. So it might contribute more, depends on what property you're looking at. So let's look at how we could do this just as an example, since maybe it's hard to visualize what polymers are. I want to talk about the difference between a number and a weighted average. Using an example could be the average mass of people in a class, okay? So let's say if we have 10 different people and they have different weights, these here are organized lowest to highest. We could ask ourselves, what's the number fraction in each mass range, and then the weight fraction, and use both of those to separately give us an average weight. So let's just step through that process really quickly. So the first thing we could do is sort of bin that data we have into different weight ranges. In this case, I've just done it in 40-pound ranges. For each of those weight ranges, we could take and count how many people fall into those ranges. And then also for the people that do fall within that range, what is the mean weight within that range, okay? So for example, we had 104 and 116. So those are our two lowest. Those are a mean weight of 110, just between those two. If we sum all this up, we end up with our total number of people and what's the total weight of all the people in the class. Okay? So those should be good sanity checks. And then what we can do is for each of these ranges, we can calculate the number and weight fraction of the people in each of these ranges. Okay. So for example, the number fraction of people in this first range is going to be the number of people in there, 2, divided by the total number, 10. So 20% of the people fall in this range, right? Now, if we look at that by the average weight, what we would see is that would be 2 times the mean, 110, divided by the total, it's going to be smaller. So the lower levels of this weight range are going to have a smaller contribution if we're thinking of a weighted average. In contrast, if we did this near the top, it would have a higher contribution. So jumping through that math, we can go and say that we can sum up how many people are in each section, what's the mean within that section, and find that, for example, our number average for the class is 188 pounds, but our weighted average is 218 pounds, okay? Just what I want to get you to understand is that when we talk about a weighted average, the higher weights are going to contribute more and push that average up higher, okay? And you'll see the same thing with polymer chains. So one thing we can do with this is talk about the degree of polymerization. This is a way of taking what that mass is and turning it into some physical way of talking about that polymer chain. So the degree of polymerization is the average number of repeat units per chain. What we're showing here is some polymer chain. And if we notice and see that the repeat unit is these 2 carbons with the 4 hydrogens, we can find that there's 1, 2, 3, 4, 5, 6 repeats in this case. Now, this idea of just looking at them and counting them isn't often how we measure that. What we really tend to do is we take what's our number average of the molecular weight, divide by the repeating unit, and we can get an idea of what the degree of polymerization is. So we care about what goes into the polymer itself. What's the repeat unit? We care about how many repeating units we have. But even knowing that, there's lots of other variety we can have within or between different polymers. One thing that can change is the molecular shape. So if you know your polymer and you even know the angles between these different atoms, on your mer, you can think about putting them together in different ways. In this case, you can put together these mers in a repeating form that makes this have a very linear type of structure of that polymer. Or you can put them together in some form that moves out of that line, okay? And the one thing I want to point out is that we're not talking about breaking bonds or anything like that. We're just talking about putting these MERs together in different combinations to end up getting different molecular shapes. So another way we can describe our polymer is, so we can describe what makes up the units, how long it is, but we can also somehow want to describe how tortuous this path is. So for example, we could measure the chain end-to-end distance. So we can say, we know where it starts, we know where it ends, what's that distance r? That's another thing we can describe about a polymer. And in addition, we can start to categorize different polymer classes. So I'm showing here 4 different ways we can do that. So on the left is what would be a linear polymer. So this is where you have these long chains. They can have secondary bonding, but those MERs are put together in these relatively straight lines. A good example of this is what's called high density polyethylene. You can build up the complexity moving one step to the right. You can have those long chains that also have little side branches that come off. This is called a branch structure. And you can see that those side branches mean that we can't sort of fill space with those long polymer chains as efficiently. And this is actually the structure that you see for low density polyethylene. So the individual bonds and the molecules in here look the same between high density and low density polyethylene. But in one case, we end up having these branches that come off. Sometimes those branches can actually connect to multiple polymer chains, in which case we describe the structure as cross-linked, with the idea that we have sort of 2 anchoring points on either side of those branches. And finally, in these first 3 examples I've given you, our material is relatively either one-dimensional or two-dimensional. So we have the straight lines and then some other dimension in the y-axis here. But we have to remember we can also have what we call network structure polymers. So these form 3-dimensional shapes. We're trying to show by showing larger and smaller little atoms here, molecule visualizations, that the material could be closer or further away. So this is a truly 3-dimensional structure. We can also talk about different ways of arranging those R units. So this is something called the tacticity, all right? So for example, those R groups can all be on the same side of that chain, in which case that's called isotactic, okay? So those R groups are all in the same place. We can have other sort of options there. Another one is called sideotactic. This is where the R groups are on alternating sides of this chemical formula, okay? There's some repeating order, but they're alternating. And we can even have situations where those R groups are randomly positioned. So in this case, there's sort of they're not all on one side, they're not repeating in some ordered fashion, they're just sort of randomly stuck in there. They still need to be done so that they keep the right chemical formula, so that there's, in this unit, 2 carbons, 3 hydrogens in one of those R units, but it's happening randomly. So this is atactic. And these are all different examples of isomers. We can also think about having different isomers that are described by their geometric orientations. So for example, this molecule on the left and the right have the same number and the same types of elements in there, with even the same types of bonds. The only difference is, for example, the CH3 and the H are positioned differently with respect to each other. So in this left case, they're on the same side. And this is what's called cis isoprene, okay? On the right side, the CH3 and the hydrogen atom are on the opposite side. This is called trans isoprene, okay? So isoprene is describing this molecule, and the cis or the trans is describing how these are oriented with respect to each other. Now, these are both actually examples of rubber. One's called natural rubber, and the other one is called gutta percha. Okay? So there's some similarity between their properties, but there are also some differences because of this geometric isomerism. Again, this is something we can use our visual material science and engineering to go see. I'm going to not skip out of my PowerPoint this time, but you can go and see how these are oriented differently. So hopefully the main message I want to get across is there's lots of different ways to classify polymers. This table or figure right here is showing you some of the different ways, and it's digging in that each of these main categories of chemistry, size, shape, and structure can also have more and more nuance as we dig down. Just taking structure as an example, we can talk about having linear, branched, cross-linked, and network structure. And then even within a given polymer type that we say it has a branch structure, we can have different isomers based on stereo isomerism or geometric isomerism. Okay, so there's lots of different options. Up until now, we've even been talking about putting together the same types of mers into these long polymer chains. That doesn't necessarily have to be the case. You can have what are called copolymers. You can put together two or more monomers and polymerize them together. There's lots of different ways you can do this. I'm just showing you a few examples on the right. So this can be done in a random fashion. So this is showing two different monomers. One is black and one is red in this image, and they're sort of put together in some random pattern. You never know which one you're going to run into next as you work your way across this. You can have more ordered type of patterns. You can have an alternating pattern where it goes between type A and B. You can have what's called a block copolymer. So this is where you get large chunks of A units, and then large chunks of B units, and then large chunks of A units. And then you can also have what are called graft copolymers. And this is where your main backbone is one type of polymer. And then you have branches that come off of polymer type B. We can also talk about the structure of a polymer in ways that are analogous to what we saw in our metals and ceramics. And for example, we can talk about the crystallinity of polymers. So we can have these polymer chains. So there's some order along the chain, but we can also have them organized so that there's some repeating unit of structure in these three dimensions. Okay, and we talk about these things in much the same way we do with metals and ceramics. We call these unit cells. That's the repeating unit cell. In this case, it's given for polyethylene. So because those polymer chains have to align with each other to give a crystalline structure, one sort of difference of polymer materials is we typically do not have materials which are 100% crystalline. Okay, the real way that polymers form is sort of shown in this visualization on the right here. So in this case, you can find regions where the polymer chains are aligned, and you would call this region right here crystalline. But nearby that, there's going to be a region where it's not aligned. Okay, and we're going to call this an amorphous region. This is a disordered region. So we're going to have these regions where we have high crystallinity and then very low or an amorphous region. And what we can do is an important characteristic of polymers is describing the degree of crystallinity. And if I look at this picture, I could think about how much of this area or what percent of this area is crystalline. Okay, and we'll see later on that some physical properties depend on this percent crystallinity, and also that we can play with this as a processing variable. We can heat treat or deform our materials to change how much of our material is crystalline or amorphous. Now, you can find a few specific examples of true single crystals of polymers. This is showing an electron micrograph. So this darker region is a polymer single crystal. It has multiple layers that have grown on top of each other. But this is really only possible because this crystal was grown very slowly and carefully. Okay, most of the polymers we see out in the real world are not going to be fully crystalline like this. So there's lots of interesting complications. One that comes about is the ways that we can mix together these ordered and these disordered regions. These semi-crystalline polymers can often have interesting structures. I'm showing one very common example here. This is called spherulite, right? And the basic idea is that in some region, the polymer chains become aligned. And we can think of this as a nucleation site for that crystal, similar to how we nucleated crystals of a metallic solid out of the liquid. And those regions that are aligned can grow out just like a crystal grew in metals. But the difference is that in between, there will be regions where these don't match up, and that will be where our material is disordered or amorphous, okay? So we end up with these fingers that are reaching out from that nucleation site. There's some sort of aligned structure in all of these spherulite growth regions, these lamellar regions, but there's also that amorphous region in the middle of it. If we look at our larger materials, we zoom out, what we would see is that these crystalline regions nucleate in a bunch of random places, just like we learned about in phase transformations of metals and ceramics, and that they grow out and they'll end up eventually hitting each other. So we can identify boundaries between these different spherulite regions, okay? And these regions right here are then analogous to those grains that we were seeing in metals and ceramics. So each of these has a slightly different orientation. And because of that, you can actually see some really cool things. So this is an example of looking at polyethylene, which has that spherulite structure with a microscope. And what they're doing is they're putting polarized light in there. And the light interacts with the crystal structure of the crystalline region. And you end up getting what these features, which are called Maltese crosses. And the orientation of that little cross depends on the orientation of the crystalline regions inside of the material. And what you can see is as you go from one region to the next, they're not oriented the exact same way. And that sort of is a representation or visualization of the change in orientation between those different spherulite regions. So moving on to properties, we can end up looking at stress strain curves and find that you can get a wide range of types of mechanical deformation for polymer materials. This plot right here is showing stress on the Y, strain on the X-axis, and it's showing that you can have very weak materials that are really stretchy. Those are the elastomers we talk about. You could have a plastic response, so something that looks elastic, yields, and then has plastic flow before it breaks. Or you can have something that's brittle. You can have something that's elastic until it breaks, right? One thing that's important to point out is that although these shapes of these curves actually look like some of the things we saw in metals and ceramics, the axes are very different. So the stresses that we're achieving in these materials are much lower. So the strengths of polymers tend to be about 10% of those from metals. So the strength is low, but at the same time, the deformation we can accommodate is quite high. So these values, 1, 2, 3, 4, your natural instinct might be to think that that's percent, but it's not. So 1 means my sample has elongated 100%, right? So this sample out here, this elastomer, has actually been pooled till it's 7.5 times its original length. That's quite a bit of deformation. So these deformations can often be 1,000% or more, and we contrast that with metals where deformations are usually less than 10%. So those different types of curves we get are actually related to these different structures that we already saw. So for example, this brittle failure type of response can come from an aligned and cross-linked polymer. So we have those long polymer chains, they have those cross-links that are connecting them. What that means is that our material ends up being relatively stiff. It's hard to pull on it and elongate it, but it's also hard to get a lot of deformation. So when we break is when we start to break those cross-links between the polymer chains. This type of behavior is also seen in network polymers. So these are those 3-dimensional polymers. Again, we have a lot of connections in these different directions. That means it's hard to deform that, but once we start to break them, this thing can just shatter and be very brittle. If we look at the plastic failure case, this is commonly seen in the semi-crystalline materials we talked about. So here we have this mixture of crystalline regions and amorphous regions. When we start to pool on this sample, what we're really doing is elongating those amorphous regions, stretching out and aligning some of those polymer chains. Eventually, these crystalline regions are aligning, and that can be connected to the onset of necking. And then finally, as we're pulling and stretching and having plastic deformation, this is when we're actually breaking up those crystalline regions into smaller blocks. Finally, at the end, we have this fiber-like structure, and we can't really pull it any longer without breaking some bonds. So this leads to a lot of interesting things that can happen in this range. This plastic deformation can actually be used to change the material properties of our polymer materials. For example, we could do what's called drawing to our material. This is just where we stretch our polymer prior to its use. And what this does is aligns those chains in that stretching direction. And this is pretty cool because this drawing ends up increasing our elastic modulus in the stretching direction. It increases the tensile strength in that stretching direction. But this all comes with the effect that we decrease our ductility. Okay? So if you want a stronger and stiffer material, you can pre-deform it with this drawing. In contrast, if we take a material that's been drawn and we anneal it, so we heat it up, it's going to want to go back to that original structure with some combination of amorphous and ordered regions. If we heat it up, that's going to decrease the chain alignment, and it's really going to reverse the effect of that drawing. So we can kind of compare this drawing and annealing to what we saw in cold working and recovery and recrystallization in metals. Moving on to that elastomer behavior shown in this green, this tends to be where we have these disordered and amorphous, sort of kinked and cross-linked materials. So as we start to pull on this, what we're doing is we're stretching out those tortuous chains right there. Eventually, they become more straight and crystalline, but they're still cross-linked. So once we get to this large deformation, we're pulling on this, we're going to start breaking those bonds, those cross-links. So one cool thing about polymers is it's relatively easy to change their properties. And a simple way you can do this is by adding in other monomers to change the properties. So you can do things like add in fillers, which end up improving the strength and abrasion resistance or toughness of your polymer. And good examples of this are things like carbon black, silica gel, wood flour, glass, and limestone powders. You can also add in what are called plasticizers. So these are done to reduce the glass transition temperature, something we'll talk about a little bit in our next few slides. But the idea here is that you really want to transform a brittle polymer into a ductile one. So if you have a polymer and it ends up being too brittle for your uses, you can just mix in some plasticizers. A good example is BEP PVC. Typically, it tends to be relatively brittle, but if your application requires it to be a little bit more ductile, you can end up adding in a plasticizing component. There's lots of different examples. I'm just showing a few here on the slide. You can add in what are called stabilizers. So these can be things that resist oxidation or protect you from UV light. So polymers, if they're put under UV light, the UV light can actually destroy some of those bonds. This isn't typically something we worry about with metals and ceramics. You can also add in things like lubricants. So this makes your polymer easier to process. You can have it slide through a die easier. You can also add in colorants. So I mentioned coatings like paint being a polymer. This is something where we have a base polymer material and we just add in bunches of dyes and pigments and it changes the color of the paint. You can also do things like add in components that make your polymer more flame retardant. So, if you needed this to be wire coating inside of your car engine, you might need to treat that differently than something that's not in that extreme environment. That processing of plastic can typically be broken down into two types of plastic. So the materials called thermoplastics can be reversibly heated and cooled. And this is beneficial because that means they can be recycled. And this idea is you can heat it until it's soft, shape it as desired, and then cool, and you can repeat that process over and over again. Polyethylene and propylene and polystyrene are all good examples of this. We can contrast that with polymers that are called thermosets. So when we heat them up, they form a molecular network through a chemical reaction. And the idea here is that if you heat this sample up after you've created this material, it doesn't melt, but you're really degrading the properties of the material, okay? So typically what you do is you mold your pre-polymer into the desired shape and then heat it to allow that chemical reaction to occur. So things like urethane and epoxy are good examples of this. The last few slides will talk about things like temperature and strain rate. So if we limit ourselves to thermoplastics for now, as we decrease the temperature, we're going to change the mechanical properties of our sample. So this is showing at 60 degrees C. This material is relatively weak and it can really stretch out quite a bit. As we reduce the temperature to 40, 20, and 4 degrees C, the material gets stronger and stronger. The stiffness goes up, the Young's modulus, but our strain to failure or our ductility is reduced. Okay. We can also get the same effect by deforming the material faster. So we can cool down our material and get this transition from right to left, or we can cool our material faster. And as you cool your material faster, you find that's the same as decreasing the temperature. So that tells us that these materials end up having very time-dependent deformation. One way to test this is through what's called a stress relaxation test. In this case, what you do is you apply a constant strain and you just hold. So maybe you strain your material 10% and then hold it. What you do is you observe how the stress decreases over time. Okay? So here in blue is showing the strain, it's constant, and the stress goes up, but then drops off over time. What's usually used to describe this is what's called the relaxation modulus. And this must be taken at a given time. And what you do is you take that stress at the time and divide it by the applied strain. Okay. On the right here, I'm showing an example of what you might see in some real data. Here's relaxation modulus taken at 10 seconds for a given polymer as we heat up the sample or to look at it at different temperatures. So at low temperatures, this value is very high. You can think of your material as a rigid solid. It only relaxes a little bit. At high temperatures, this value is really low. It means that our material is basically behaving like a viscous liquid. It relaxes that stress very, very quickly. And in between, we have this drop off of that value in this transition region. You can use this transition region to define what's called the glass transition temperature. It's where we have that change from a rigid solid to a viscous liquid. And this glass transition temperature could be something you go and you measure and calculate for your given polymer. So for example, this polyethylene, these numbers are negative numbers, which means that at room temperature, you're going to be way above that, and your material is going to easily deform. In contrast, PVC is above room temperature, so this material will be relatively rigid and solid at room temperature. We can also talk about things like fracture with polymers. Most of the things we mentioned are quite similar to metals. I just want to mention one thing that sort of sticks out, and that's this phenomenon called crazing. So we mentioned that you can, as you deform polymers, you can get an alignment of those crystalline chains. As the crack is growing, this can especially happen around that crack tip. You end up getting these aligned chains, which are just those fiber type structures from the spherulites, and they form and surround that crack. Now, as the crack breaks open, you'll start connecting those different microvoids and developing the crack just like you did in a metal, but you end up keeping to align those features around the crack tip. What this often means is that you find that your material is hazy or has a different color around a crack tip. And that's just a sign of those polymer chains aligning. So with that, let's summarize. So polymers have some limitations. Their modulus, strength, fracture toughness, and temperature of application are generally small, and their deformation can be time and temperature dependent. We mentioned a lot of different kinds of polymers. I'll just remind us that we mentioned thermoplastics, which have relatively low modulus strength and application temperature, but a larger fracture toughness. These are easy to form and recycle. Elastomers have large reversible strains, and thermosets have relatively small fracture toughness, but higher strength and modulus. Okay. One thing I want to point out is that, we did a relatively quick introduction to polymers. This could be a whole field you study for the rest of your life. So I'm not talking about everything in this lecture. But another good resource for you is table 15.3. It talks about a lot of different applications and trade names for these different polymers. It will help you sort of get a sense of where you may have seen these different examples that we talked about today. All right. Thank you very much for your attention. Looking forward to seeing you soon in a Q&A session where we can discuss this together.